Hello and welcome back. Let's do last couple of examples for u-substitution. So again, when we stare at the integral that we want to take from -1 to 2, it looks a little bit complicated. Right away, I will mention two things though. One is we can in fact use u-substitution in here. When we stare at this, we see that okay, we've got an x cubed minus 9 sort of inside this function. So that seems like a reasonable u-sub to put that inside. And one other reason why this seems reasonable is that when I take the derivative of x cubed minus 9, I'll get 3x squared, and if I want the differential, I've got to add the dx at the end. And this x squared dx is inside of my original integral as well. So this would be a good u-sub since both u and du are going to be inside of our integral. The one thing I'll mention though is that this is a polynomial, x cubed minus 9, and I could raise that to the third power. So I could just take x cubed minus 9 times x cubed minus 9 times x cubed minus 9 and FOIL that out forever, and then multiply everything by x squared, and I could just have a big giant polynomial, and that would be reasonable to take the integral of as well. However, it's going to be a lot of extra work. So I'll use the u-sub to make this a bit shorter. And since the x squared dx are sort of together, I'm going to rearrange this just a little bit so that it's a bit easier to see. I'll move the x squared to the other side. We've got x squared dx. And now I can see that I have my x squared dx, but let's solve for that. I've got x squared dx. I'll divide both sides by 3, so this will be 1/3 du. And now I can come back and make my u-sub. So this is going to be the integral from -1 to 2 of, okay, so x cubed minus 9. That's my u. That's going to be raised to the third power. And then x squared dx is 1/3 du. And then from here, again, if I have a constant 1/3, I can pull that out of the integral. And then I have u to the 1/3, so I'll raise it to the 1 higher power and divide by that power. And that's pretty much it. And then I'll have to plug in my bounds. And my bounds were originally in terms of x. So I have to plug in x is equal to -1, and x is equal to 2. So let's plug those guys in. So 1/3 times the 4th is 1/12. And I'll plug in 2. So this would be 2 to the 4th power minus what I get when I plug in -1. Oh, I just did exactly what I said I shouldn't do. I apologize, I made a mistake. U here, I need to plug in x. That's very important. So again, I'll have 1/12 after I multiply the 1/3 and 1/4. But this is going to be x to the third power minus 9, all raised to the 4th power. Hoofda. Okay, so x is equal to -1 and x is equal to 2. So now I can plug in my x is equal to -1 and my x is equal to 2. I just about made a huge mistake. So it'll be 1/12 times 2 to the third power minus 9, all raised to the 4th power. And then we'll plug in -1 into here. So we'll have 1/12 -1 to the third power minus 9, all raised to the 4th power. And this is going to be a little bit silly. 2 to the third power is 8, minus 9 is -1. So -1 to the 4th power is just 1. So the first part is going to be 1/12. And we're going to subtract. So -1 to the third power, -1 times -1 times -1 is -1. And -1 minus 9 is going to be -10 to the 4th power. So -10 to the 4th power is going to be 10,000. So is going to be 1/12 minus 10,000 twelfths. And that's something we could simplify this to be, what, negative 9,999 twelfths. I can simplify it further. Maybe I should. If I divide both the top and bottom by 3, I have negative 33,333 fourths. So there's our simplified fraction. But you can see that the end part was just plugging in x into our function, but we needed to remember to substitute our x back in for u. And let's do one final example of u-sub. We have the integral from -1 to 1 of x e to the x squared dx. And again, what we're looking for is a function that we can plug in so that its derivative is also popping out. So we need to find u and du. And here we have our x and an e to the x. So maybe I want my u to be e to a power, maybe like e to the x squared. But the derivative of e to the x squared is going to have another e to something power. And I don't have two of those in here. So the derivative of an exponential is going to be itself with an extra bit. So I don't want u to be e to the x. However, if I just take it to be that exponent, the derivative of x squared is just 2x. And then if I want the differential, it will be 2x dx. And I have an x dx in there. So let's rearrange this just to make sure that it's really clear. I'll move the x e to the x squared out front, and then I've got x dx out back, and I can plug in my u, and my du is going to be out here. I'll solve for x dx though, since that's what is going to substitute. So it's going to be 1/2 du after I move the 2 to the other side. This is going to be the integral from -1 to 1 of e to the u times 1/2 du. And that's pretty nice. So the 1/2 I can pull out of my integral. Constants, the constant times the function, I can just pull that constant out. And then the integral of e to the u is e to the u. So that's a pretty straightforward integral to take. And then I have to plug in x is equal to -1 and x is equal to 1. But again, I'm plugging in x's in here, not u. So I'll resubstitute x squared in for u, e to the x squared. And I'm going to plug in x is equal to -1 and x is equal to 1. So this is going to be 1/2 e to the 1 squared minus 1/2 e to the -1 squared. And what you'll notice is that 1 squared is 1. So this is just 1/2 e minus, and then -1 squared is also 1. So 1/2 e minus 1/2 e is 0. And so that means that as we take the integral, the area above the x-axis and the area below the x-axis are going to be equal, and they're going to cancel out. And if you graph this, you can see exactly that. X e to the x squared is going to look something like this. This is a rather poor drawing, but if we look at the area in there, the area below is going to be equal to the area above, and they'll just cancel out and give us 0. So that is u-substitution in a nutshell, and we'll do integration by parts in the next video.